All right, so I'll be chairing this session, and it's a great pleasure then to introduce Peter Koellner of Harvard University. So Peter's one of the foremost philosophers of set theory these days. He's done important work on most aspects of set theory, really. So on reflection principles, on the question of absolute undecidability, Godel's program, wood and stuff, and he'll be speaking to us now about Godel's disjunction.
Well, thanks, Oprah, for organizing this and inviting me, and thanks, Charles, for being Charles. I first met Charles 11 years ago.
Just to the mic.
A little bit louder, anyway.
Is this okay?
No, it's just to the mic.
That's just for recording. You want to record it? Okay. How's that? Is it picking it up?
No.
I know it's not going over there, but is it getting picked up on the recorder?
No, a little bit higher.
We tried this earlier. I didn't have to attach it to my nose. How about now?
Yes.
That's better? Okay, good. So I first met Charles 11 years ago. Just over 11 years ago. But I knew his work much earlier than that. I studied in graduate school when I was at MIT. I never took a class with him, but toward the end of graduate school, I was encouraged to go and talk to him, and I did. And during that conversation, we talked about reflection principles, and he told me that Harvard was hiring, and he encouraged me to apply. And then we became colleagues, and we've gone to each other's seminars. So I've gotten to know him really quite well as a colleague and as a friend. When you read a philosopher, you enter a certain framework that has certain fundamental notions, guiding questions, background assumptions, and approaches to resolving those questions. And usually when I enter such a framework, the first thing I want to do is get the hell out of it. But when I read Charles's work, I feel incredibly comfortable. The questions he asks seem to be the right ones. He's clear about his background assumptions. He doesn't overstate his claims. And I found that to be really comforting. So when I read other people who sort of make me want to jump out, I just pick up Charles's work and I feel much more at home. So I've tried to build on it in my own work, and it would have been natural for me to talk to you about evidence and reason in mathematics, but I've talked about that a lot, and I've talked to Charles about it a lot, so I thought I'd talk about something completely different. So I'm going to talk about Godel's disjunction, and what I want to do is examine the concepts of relative provability, absolute provability, and truth, and their interrelations. And one aim will be to get clear on the question of whether the incompleteness theorems have implications for the question of whether the mind can be mechanized. Now, I have scare quotes around that because I'm not exactly sure that I understand what it even means for the mind to be mechanized. I'll say something about that. Godel himself thought that his incompleteness theorems did indeed have such implications. So let's first review his theorems and then turn to the disjunctive conclusion that he draws from it. Now, I should mention a meta comment. This talk is going to be a bit technical and everybody's exhausted. So what I want to do is give you a guide. You shouldn't pay too much attention to the formalism. I'll tell you what the main points are and when you should wake up. Just take naps in between and I'll give you the highlights. So assume that PA is consistent, then there's a statement which is independent of PA. Strictly speaking, this is Rosser's theorem. And the second incompleteness theorem tells us there's a particularly interesting statement that it can't capture, namely the statement that asserts it's consistent. And it's important to note that these theorems are perfectly general. They apply to any sufficiently strong system. For example, they apply to systems weaker than piano arithmetic. they apply to ZFC, and they apply to ZFC plus large carbonyls. Now, does that, now I'm going to turn to absolute provability and the disjunction. So, although the incompleteness theorems show that certain statements are unprovable relative to a system like PA, it's unclear whether they show that they're absolutely unprovable. That is, unprovable with regard to any set of well-justified axioms. Godel certainly thought that his theorems didn't show this. In fact, as soon as he stated the theorem, he said, they don't show this, so he guarded everyone against it. He said, these statements are not at all absolutely undecidable. Rather, one can always pass to a higher system in which the sentence in question is decidable. In particular, for example, it turns out that if you go from arithmetic to analysis, you can settle the consistency sentence, and if you go to the next layer, you can settle the consistency sentence, and it continues like that. So this raises two questions. First, does absolute provability outstrip all forms of relative provability? What we've shown is that if you pick one form of relative provability, then you're going to get sentences which are going to outstrip that. But there's a bit more of a subtle question of whether it outstrips all forms of relative provability. You can hide the parameter. And then there's the question, does mathematical truth outstrip absolute provability? So I'm interested in the relationship between these three notions. Formal provability, relative provability, absolute provability, which I'll write as a K for reasons which will become clear later, and truth. And we're going to have that we're interested in systems which give us things which are absolutely provable, and everything that's absolutely provable is going to be true. So the question is, what is the relationship, further than what's written on the board, between F, K, and T? Now, the first question, does absolute provability outstrip all forms of relative provability, has a variant. Does the idealized human mathematician outstrip the idealized finite machine? And these questions are connected. So Godel claimed that one of two things holds. Either mathematics is incompletable in the sense that its evident axioms can never be comprised by a finite rule, or in a variant mentalistic formulation, the human mind infinitely surpasses the power of any finite machine, or there exist absolutely undecidable sentences. So what he's saying is either the idealized human mind surpasses the finite human mind, or there's mathematical truths which you cannot resolve with absolute provability. In other words, either K, this is a model of the idealized human mind, outstrips all the machines, or there's truths which can't be reached by K. Okay, so in other words, either absolute provability outstrips all forms of formal provability, or you outstrip a Turing machine in your idealized sense, or there exist absolutely undecidable sentences. And he thought that he could prove this. He called it a mathematical fact, he called it a theorem. And he thought that each of the disjuncts was of philosophical significance. So the first disjunct says something important about the nature of the mind. The mind outstrips any machine. And the second disjunct says something important about mathematical truth. Mathematical truth is unreachable by the idealized human mind. And that, he thought, would make a case for realism. So either reason outstrips computation, or truth outstrips reason. That's a pretty significant philosophical conclusion. And he thought that he could argue for it. Now, what I'm going to do in the rest of the talk is make this precise. I want to pull this question into a framework where we can be explicit about our background assumptions and actually prove definitive results. And I'm going to concentrate on the first disjunct, that the idealized human mathematician outstrips all Turing machines, because that's the disjunct people have been trying to prove. Lucas, Penrose, the people who are against artificial intelligence. But now I just want to say something about the idealizations involved and why I'm a little bit skeptical about the meaningfulness of the entire question, which is a bit weird to do. I mean, you always tell undergraduates never to say something disparaging about their project, and I'm going to tell you that everything I say from now on may be just completely meaningless, but I feel like I have to do that. So the reason I'm skeptical about the notion of the idealized human mathematician is it's unclear which lines along we're generalizing. So let me compare. If you consider an idealized machine or a frictionless plane, you can make sense of it. So to understand a frictionless plane, we just look in terms of the physical model where we take friction and decrease it to 0. So we have a grip on it. We have an approximation. That's the line along which we're generalizing. With a finite machine, we idealize it by relaxing certain constraints, time, space, and we forget about friction, wearing parts, and things like that. So again, we have lines along which we can idealize because we have good models. We have models of friction and we have models of machines. But when it comes to the human mind, what does it mean when we consider the idealized human mind? The trouble is we don't have a good model of the human mind. So this is really an unknown. And one point where I can tie this up with Charles's work is what he talks about in his paper on what we can do in principle. So he has this fantastic example. He considers the possibility of whether Charles Parsons can, in principle, jump over the Eiffel Tower. Now, it seems pretty clear that no matter how much training Charles did, if he went to Paris and learned parkour, he would never get to the point where he could jump over the Eiffel Tower. It's probably not even possible for an animal to jump over the Eiffel Tower. I mean, there's, biophysical constraints. And if you were to change Charles to the point where he didn't have those biophysical constraints, it's quite unclear that he would still be Charles. And if the Eiffel Tower isn't big enough, then pick something bigger, like Jupiter. Several diameters greater than the observable universe. Not going to jump that far. So it's unclear whether Charles can do that. Okay, then consider something like this. Can Charles perform large computations? Well, 100, 1,000. But is it in principle possible for Charles, the person sitting there, to perform a computation of length Skew's number? Skew's number is big. It's easier for him to jump over the Eiffel Tower. So there's this element of idealization which is difficult. Now, we can make sense of him computing the Skew's number if we model him as a Turing machine. But if we model him as a Turing machine, then we've erased the question. So, because he couldn't possibly have a Turing machine if he is a Turing machine. So we've got to model him a different way. So how do we model him? Well, it's as though we're studying the angelic mind, where we really can't say anything more about the angelic mind than just it's something. And we're asking whether it can be modeled by a Turing machine. But now I don't know what we're talking about. Okay, so that's why I'm skeptical of the whole question, but I'll move on anyway because I think that interesting things can be said. This Godel referred to the disjunction as a mathematical fact, and people set out to prove the first disjunction. So let's look at this notion of absolute provability. It's a bit difficult to model because early results show that you can't treat it as a predicate. K here is for knowledge in the idealized sense, and it's also for something else. Someone saw this talk, and they said that it reminded them of Kafka because you start out with this outlandish assumption, and then after that, everything else follows rationally. We made the first move, and now we're going Okay, so here's the first bit of rational stuff. So Montague showed that if you try to treat knowledge as a predicate and don't pay too much attention to this, and you have some fundamental principles, like if you know something that it holds, okay, then you get an inconsistency. So people retreated. They said, okay, let's not treat it as a predicate, let's treat it as an operator. And that's what we'll do. We'll treat it as an operator. And we're going to look at a system called epistemic arithmetic, which is due to Stuart Shapiro and Bill Reinhardt. And the axioms fall into two categories. So we're going to have axioms that concern knowledge or absolute provability, and axioms that concern arithmetic. And I won't get into details. Well, I guess I will. The basic axioms of absolute provability are going to be this, that you know all logical validities, and things like this. If you know that phi then psi, and you know phi, then you know psi, and so on. Now, this assumption that you know all logical validities is a pretty big assumption. It's part of our idealization. Some of those logical validities are really long. Okay? And Charles is not going to know them, like a validity of length is used number. So we're really stacking the assumptions, but that's good because we're trying to assess the claim of whether the idealized human mathematician can be modeled by a Turing machine. And so I want to give the opponent as much as I can. I let them have all of logical knowledge. Okay. And then I'm going to add a truth predicate. And at first, the truth predicate is just going to be the standard Tarski one, where you don't have truth applying to itself. So you're avoiding the paradoxes that way. And so we have this system. So in this system, you can prove versions of the incompleteness theorem, as Reinhardt showed, which are absolute. They concern not just formal provability, but absolute provability. And Godel kind of saw this. There's a whole collection of prose quotes that I'm going to give you, and then I'll show you that you can actually make it rigorous. So for it is impossible that someone should set up a certain well-defined system of axioms and rules and consistently make the following assertion about it. All of these axioms and rules I perceive to be correct, and moreover, I believe that they contain all of mathematics. If someone makes such a statement, he contradicts himself. For if he perceives the axioms under consideration to be correct, he also perceives, with the same mathematical certainty, that they're consistent. And hence he has a mathematical insight not derivable from his axioms. It's a good informal argument, and it's provable. So if you have a system that includes just the base theory, epistemic arithmetic, and you consider some candidate system, which is your candidate for a model of absolute provability, and you know that it's sound, so you know that if it outputs something, then that thing holds. Then there's a sentence such that you know it, and you know the system doesn't know it. Okay? So this is something the idealized human mathematician can do. It goes up to any system and says, you're correct, and then it applies the incompleteness theorem, and then it gets something that the system can't have. And there's another version of the second incompleteness theorem, but I'll just go on. So now I want to talk about Gödel's disjunction. Can we make it precise in this setting? Yes, we can. And it'll be useful to consider three mechanistic theses following Reinhardt. The first one says, these E's here are just indexes of Turing machines. The first one says there is a Turing machine such that you are identical to it. You're going to be the idealized human mathematician. There's a Turing machine such that you're identical to it. The second one says, you know there's a Turing machine such that you're identical to it. And the third one, de re de dicto distinction, says there is a Turing machine such that you know you're equivalent to it. These last two are very importantly different. In fact, I see the ambiguity between these two all over philosophy. And they actually come apart. Okay, so I guess I should stop for questions. Are there any questions about these three? So remember, the disjunction says either use the past Turing machines, or there's absolutely provable sentences. Absolutely unprovable sentences. And I'm trying to model the first disjunction. There's a weak version which just says there is a machine such that you're equivalent to it. A strong version which says that you know it. And a super strong version which says there's an index such that you know you're that machine. See, it's possible that you could know that you're a machine. It's just not know which one. I'm in a position where I know I'm a machine, but I can't figure out my code. I don't know which one I am. So these are increasingly strong. So for the disjunction, I'm going to take the first disjunct to just be the negation of the first one. So it's not the case that there is a machine such that you're equivalent to it. And the second disjunct, absolute unprovability, will just say there's a truth which is neither knowable and such that its negation is not knowable. And the disjunction just says either the weak mechanistic thesis fails or there's an absolute undecidable sentence. And as a theorem in the system, EAT, we can prove the disjunct. So it looks good, right? Godel had an informal argument for it. We've articulated the background assumptions on the fundamental concepts involved, and we can prove it. Now you might be thinking, okay, so that probably looks good for Lucas and Penrose, the people who've been trying to argue that we're not machines. So we've proved a disjunct. Can we prove the first disjunct, or can we prove the second disjunct? So which disjunct is true? So Lucas and early Penrose gave an argument purporting to establish the first disjunct. And the argument's actually an informal version of that proof of the absolute incompleteness theorem, the one that Godel informally articulated. However, as many people pointed out, they neglect to notice that what the theorem provides you with is a conditional. Go back to it. This is a regimentation of the discussion. And people don't even talk about these systems when they discuss this topic. So the theorem says that if you know that whatever the system produces is correct, if you know that it's sound, then you outstrip it. Then there's something that you know that it doesn't know. It doesn't follow that you can outstrip any Turing, any machine. You have to first know that it's correct. So, as I say, however, as pointed out by many logicians, they neglect to notice that the theorem provides us with a conditional. And to arrive at the consequence that you're not a machine, you need to discharge the antecedent. You need the additional premise that the mind knows that the system in question is sound. So that shows that that first argument of theirs doesn't work. So this particular argument for the first disjunct, that you're not a machine, fails. But perhaps there's another argument. It's always the thing, you have this back and forth. You say, this argument for that thesis fails, and this is wrong. Maybe there's another argument. What you'd like to be able to do is show them that there's no other argument at all for that thesis. And you can do that because we're in a mathematical setting. So Reinhardt showed that it's consistent that all of those assumptions about absolute provability and truth are consistent with the weak mechanistic thesis. So you're never, on the basis of these assumptions alone, going to prove the first disjunct. Now, at the opposite extreme, Reinhardt showed that it's inconsistent for there to be an index such that you know you're that machine. So that's probably what people are getting confused about. What about the other one? Well, there's a subtle issue that Godel appreciated a long time ago. However, as to subjective mathematics, by which he means what you can do, absolute provability, K, it's not precluded that there should exist a finite rule, one of those indexes, producing all of its evident axioms. However, if such a rule exists, we with our human understanding would certainly never know it to be such. That is, we could never know with mathematical certainty that all propositions it produces are correct. Okay? But can know that there is a machine such that you're equivalent to. You just can't know which one. Okay, so this precisely articulates a lot of the things that people were saying but weren't establishing in the literature. So these results pose a limitation for any argument that purports to show that the first disjunct of the disjunction holds, for they show that any argument must invoke assumptions beyond those of BAT. Now remember, in BAT, we gave the opponent a lot. We're giving them an idealized notion of the human mind. We're allowing it to know all logical validities. It's really powerful. And even with all those assumptions, they can't prove that that idealized human mind is not a machine. So I think that that ends the case for Lucas and early Penrose. And now I'm going to go on to Penrose's new argument. But I should maybe pause there for discussion because I have half an hour.
You're probably aware that Banasra published an article on the subject where he discussed this business about from a machine I can't know which one. That's the point you made. But you might have made this before Reinhardt.
Yeah, he made that point quite early on. It was before Reinhardt's papers.
God, the Devil and Godel was the
Yeah. But, you know, none of it was proved. That's the thing.
He has it's a formal argument. I don't know if he does. He has a number of epistemological axioms. You know, maybe it's not as formal as this thing, but it's not verbal. It's an actual.
The proof that these two things are consistent were not in his repertoire. These are not so bad. This one's very hard. I mean, he made the claims, and it wasn't in the formal, it wasn't in a precise framework, and it took a lot of work to actually get theorems. But now we have theorems, and so. But no, he's on the right track, just like Godel was. Godel stated the disjunction and drew this distinction. But now the case is, I think, sealed.
Must it be an idealized human mind? I mean, if Godel is Platonism, if he's serious about the Platonism, and we are beings who intuit or have grasp of abstract objects. We don't have to think of ourselves as idealized. That's just a capacity we have.
Well, if I'm proving negative results about this idealized notion, so they're going to apply to anything less idealized. But are you saying that maybe we already are idealized human mind?
No, we don't have to take up the issues about idealization and jumping over the Eiffel Tower and all that stuff because we're already beings who and then there's a lot of work that's going to have to go into saying how it's possible that human minds could have access to abstract objects, but we are beings who have that access, and so we don't have to think of ourselves as idealized. We can just do that.
That's a different topic, though. I'm talking about outputting mathematical theorems. And we have to think of ourselves as idealized if we're going to output mathematical theorems, which are of length Hughes number. I mean, no matter how idealized you or I may be in terms of understanding abstract objects, in terms of our ability to do computations, we're not so idealized.
It's about provability.
Yeah.
Very idealized provability.
We're very finite beings on that front.
Sure, but there's a possibility of deciding like open problems, right? Where on Godel's picture, we decide open problems because we've got some access to more mathematical reality than we had before.
But the number of open problems that you can settle is less than 10 to the 10 to the 10, because that's greater than the number of fundamental particles in the physical universe. That's where the Eiffel Tower thing comes in. I mean, yeah, we have these flashes of creative insight and things like that, but we're still very finite.
Right, that's right. And so we're finite beings who have access to abstract objects, and that's the reason for thinking that we can solve certain kinds of open problems and do solve certain kinds of open problems.
but you cannot output a theorem of length the skews number. No matter how, yeah, but a Turing machine can. So in terms of that output, you're already outstripped by a Turing machine. So I have to idealize you in order to get the question off the ground.
Okay. Well, then the argument would be that you're not a Turing machine because you intuit abstract objects and Turing machines don't.
Yeah, I mean, look, yeah, that's a different thing.
Okay.
You could, you know, you could do poetry, Turing machines can. Fall in love, Turing machines can. But
Not yet.
there's other arguments. There's other arguments. See, my assumptions on EAT just have things about piano arithmetic, no ability. They don't have anything like can intuit an abstract object or can have a romantic encounter, you know, or anything like that. I'd have to strengthen the theorems considerably to get negative results on that.
Let's table this one, maybe we
Yeah,
come
sure.
back to it,
Yeah,
because there's
sure.
some,
No
might be some
problem, yeah.
interesting things to say.
Okay, so Penrose's new argument. The above results take place in the system EAT, where one treats the paradoxes of K by treating it as an operator, and the paradoxes of T by treating it as type, so not allowing truth to apply to truth. Godel didn't think that the typed approach was an adequate approach to either. And moreover, he held if one could clear up the intentional paradoxes, one would get a clear proof that the mind is not a machine. So Godel actually thought that you could prove the first disjunct. You believe the first disjunct and you believe the negation of the second disjunct.
Is it an idealized mind or an ordinary mind?
Well, it's the idealized mind.
But ordinary people can be machine, just ordinary people.
Well, I mean, I'm at this stage, and we're in the passive now, so I'm idealizing. I'm just dealing with idealized mind, so it's that leap, the Kafka leap. So here's Penrose's new argument, and it's a bit of a tongue twister. So, but I think it's a fascinating argument, and I don't think it's been properly treated. So I'll read it. Though I don't know that I necessarily am F, I conclude that if I were, the system F would have to be sound. And moreover, F prime would be sound, where F prime is that system supplemented with a further assertion I am F. I perceive that it follows from the assumption that I am F that the Godel statement for it would be true, and furthermore, it would not be a consequence of F prime. But I've just perceived that if I happen to be F, then the Godel sentence for the strengthened system would be true, and perceptions of this nature will be precisely what F is supposed to achieve. Since I am therefore capable of perceiving something beyond the powers of F, any candidate system, I deduce that I cannot be F after all.
I assume that the first occurrence of G F prime should be G F? And in the 1, 2, 3, 4,
No.
5?
No,
F prime each time.
I think so. Because you're getting that the next system is sound.
Okay, good. I got it.
This argument has come under criticism. For example, Lindstrom, Chalmers, and Shapiro have pointed out that it treats knowledge as a predicate. If it treats knowledge as a predicate, then you get inconsistency. And Shapiro observed that it requires an unrestricted truth predicate. And there's problems with that. However, there are various ways of overcoming each problem. One can treat K as an operator, as we have, and there are ways of treating truth as untyped. And that's what we'll do. So let us be as charitable as possible, because the strength of the criticism is proportional to the degree to which it's charitable. So you can formalize this argument, and I don't want you to look at that because you're going to fall asleep. But you can formalize it in this language, and you use some inference rules. Use this rule T in, and it continues, and then bang, at the end you get that you're not that machine. And it uses this K intro. Okay? So Shapiro's right. When you formalize the argument, truth is applied to K is applied to T, so truth is applied to T, and K is applied to K. So we need a type-free theory of truth to get this argument to go. And the key principles that are used are, if something is known, then it's true. T in, which says that if you have phi, then you can go to T of phi, and then K intro, which says that if you establish something, then you can establish K of that. Now, what I want to do then is try to find a system in which all of this works, and the Penrose argument goes through, and Godel's hope of an argument for the first disjunct goes through. Now, when you're shopping around for theories of type-free truth, there's lots of them, and they fall into three classes. There's the ones that use non-classical logic, there's the ones that use classical logic without gaps, and there's the ones that use classical logic with gaps. Okay, the first ones are subsets of the third, and what I want to do is look at all possible ways of defending truth and show that there's problems with all of them. But that would take a long time, so I'm going to be schematic. So the Penrose argument cannot be implemented in non-classical logic. Those versions for such approaches, nothing like sustained ordinary reasoning can be carried on. It's a quote from Pfefferman. And moreover, those systems are subsystems of the systems I'm going to consider. So anything I say about the systems I consider will apply to those. So without loss of generality, we can focus on the systems I consider. And it cannot be implemented on the approach involving classical logic without gaps, since granting minimal principles of truth, there's only one system that involves that fundamental rule, T in. If you have phi, then you can go to T of phi. Namely, the system which renders all statements true. This is a theorem of Friedman and Scheer. They looked at a classification of all those kinds of theories of truth. There's only one that has this rule that Penrose uses, and it collapses the distinction between truth and falsehood. So that leaves us with the third approach. Okay? So without loss of generality, we can look at the third approach. Now, there's a very nice example of one of those systems in the third approach due to Pfefferman. It's his latest version, I think it was 2010. And I'm going to focus on that one. It's called DT for determinate truth. And now the key point is we're dealing with a setting where truth applies to itself. So you can form sentences that say, this sentence is false. And that sentence is paradoxical. So it's going to have to be evaluated as indeterminate. And that's what the Axioms capture. They have an additional predicate, D, for determinate. And in the system, you're going to be able to show that the liar sentence, the sentence that says this is false, is just not determinate. Okay? It's going to be neither true nor false. DT is just shorthand for saying that it's not true and its negation is not true. I mean, DT is shorthand for it's true or its negation is true. Okay, and I won't go into the details of this, but it's really just a conditional version of the Tarskian axioms. So you have things like, for any sentence, if its negation is determinate if and only if it's determinate. And a disjunction is going to be determinate if and only if both the disjuncts are determinate. Okay? And then for truth, you just condition. You say, if a sentence is determinate, then its negation is true, if and only if it's not true. So these are just the natural things, but you condition on determinateness. It's a very elegant system, and Pfefferman showed that it's so elegant that you get just what you would want. You get the conditional Tarski biconditionals. So if a sentence is determinate, then truth is such that it holds of that sentence if and only if the sentence holds. Follows that the liar sentence is not determinate. So it seems in the system you can kind of pinpoint the pathologies, and then with the good sentences, like language of arithmetic and physics, you can just go on and use the truth predicate without embarrassment. Now, it'd be natural to just take this theory. We've got a nice theory of truth, and join it to our earlier theory, the nice theory of absolute provability, and then just add the rule that says if something is known, it's true. Well, unfortunately, the system is inconsistent. Okay, and that's where I concluded a long time ago. Like, I've been thinking about this for 25 years on and off, and at one point I got to this point, but it didn't feel satisfactory because, you're trying to criticize Penrose, and you say, look, I can formalize your argument in the system. He's like, great. And then you say, unfortunately, it's inconsistent. So I wanted to be able to give him something better. You might fall for the first part where you adjoin the theory of truth with the theory of knowledges. They're both very plausible, but when you put them together, you get an explosion. Oh, and the reason is simple, but I won't go into it. We only have 18 more minutes. Of course, once we have indeterminate sentences, well, I guess I will go into it.
We actually do have exactly 18 minutes to the end of this session, by my watch. Of course, it's not my phone.
The reason is simple. This original system has that you know phi for all logical validities. Now, the liar or not the liar is a logical validity. So you know it. But if you know it's true, it's determinate. But a disjunct is true if and only if both disjuncts are determinate, so there's a problem. Okay, now you might say, well, that's kind of silly. You shouldn't have thrown in that axiom that you know all the logical validities when it's got one of these pathologies in it. So we should have conditioned all of our knowledge axioms on determinateness, just like we did with truth. And surprisingly, when you do that, something interesting happens. You can circumvent the limitative results of Godel, Montague, and Thompson and actually treat K as a predicate. Now this is good for Quinians, right? Quinians don't like operators. They like predicates. The Godel-Montague theorem shows you can't treat knowledge as a predicate. So what do? Well, the problem is that it's looking at things too narrowly. Once you broaden the view and allow the liar sentence and tie it with the theory of truth, then you can treat knowledge as a predicate. If you just look at knowledge in isolation, you can't treat it as a predicate because of the paradoxes. But if you look at knowledge together with truth, and you connect them by saying everything you know is true, then the solution you give for the paradoxes on the truth side is going to induce a solution on the knowledge side. So I think what we should do is we should make sure that all of our beasts have one head, truth, solve the puzzles there, and then tie other notions like knowledge to it, and then induce the solution. And when you do so, you can treat knowledge as a predicate, so the point is not happy. So the system DTK just conditions the knowledge principles. Instead of saying, if you know it, it's true, you say if it's determinate, then you know it's true. Instead of saying that if you know X, then Y, and you know X, then you know phi, you just say, well, if all the ingredients are determinate. Very natural. You don't want the liar to get in there and ruin things. And we have these two rules that if you've established a sentence and then it's determinate, then you can establish it's known, and likewise for truth. And there's a theorem, so that system is consistent. Okay, it's a fixed point argument, it's not hard. None of the mathematics in this is difficult. It just follows Pfefferman's proof. So we have a consistent system that has type-free truth and knowledge, now both predicates, just as Penrose has. Okay, and in this we have absolute versions of the incompleteness theorem, so we can recapture a lot of the stuff that was done earlier. You have that, suppose in the system you can show that a given candidate system is correct, then you can show there's a sentence such that it doesn't know it. So you can outstrip the candidate sentences that you know are correct. And similarly for the second incompleteness theorem. So back to Penrose. We have this theorem of Pfefferman's that if a sentence is determinate, then you know it's true if and only if it holds. So we have these rules, T out and DT in. But he needed these three rules, and although we have the first one, we only have these ones when they're conditioned on determinateness. So what's going wrong with this system? He's presupposing that the sentences he's got along the way are determinate. if they're determinate, then the argument goes through. But we have to be careful now, right? So he applies these rules to these two sentences, and actually, these two sentences that he applies them to are provably indeterminate. So he's given an argument, but he's written down statements that are by his own lights indeterminate. In fact, I'm going to say something a little more strong than that. So that shows that that particular argument for the first disjunct fails, just like with the Lucas case. Okay, so that argument fails. But perhaps there's a different argument. Now, you have to distinguish various versions of the mechanistic thesis. And what I'll do is I'll just use a subscript L, where you vary the language. And the two main examples I want to consider are the case where you're only quantifying over sentences which are determinate, and the case where you quantify over any sentences. And likewise, we're going to have versions of the absolute undecidability statement and the disjunction. So they have quantifiers over sentences. The first you just quantify over the good ones, the ones that are determinate, like in PA. The second you quantify over them all. So a theorem, you can prove the disjunction in the system. This is the full disjunction, where you're quantifying over even crazy sentences like the liar. And you can prove that the disjunction, when it's restricted to the determinate sentences, you can prove that that statement is determinate, which is good. It's not a pathology. So you're not dealing with a pathological statement. So you know that statement, you know the disjunction. However, it's consistent that the determinate version of the in other words, you can't prove the second disjunct when the second disjunct is determinate. And you can't prove the first disjunct. So you can prove the whole disjunction, you can prove that it's determinate in the determinate case, but in the determinate case, you can't prove either disjunct. Okay, what about the indeterminate case? Well, if you look at the full version, then everything falls apart. Everything in sight is provably indeterminate. So the situation is, we have a system in which you can write down the argument that Penrose gives. The argument he gives fails. Then we're thinking, well, maybe there's another argument. And we have to be careful. There's two versions of the disjunction and its disjuncts. The determinate version, and then that's a restricted version, and then the unrestricted version. In the unrestricted case, he's dealing with a sentence which is not determinate. It's provably neither true nor false. Okay? It's a pathological statement. So he's setting out to establish a statement which is pathological by his own lights. In the second case, the system cannot settle either disjunct. Moreover, you can add other principles of knowledge, and these results are preserved. So you can add that you know that if you know something, then it holds, and things like that. You can strengthen principles of knowledge. You can take anything that people in epistemology have written down as a principle of knowledge and add it to the system, and you're still not going to be able to prove either disjunct. And moreover, this was just a representative system out of the ones that had a chance of proving the first disjunct. So it looks like it's a pretty comprehensive thing. Now, how do I want to conclude? Well, first of all, in summary, as I just said, I'll say it again, DTK cannot prove the determinate versions of either disjunct, and in the general case, each disjunct is provably indeterminate. Now, we've taken the step into Kafka's castle. Everything proceeded rationally. Now I want to stand back and just make a disjunctive claim. The disjunctive claim is that either the fundamental notions involved in the statement, the mind can be mechanized, are suspect, or if they're not suspect, then there's no way of establishing the first disjunct. In other words, the first disjunct and the second disjunct are good examples of statements that are absolutely on the side of them. Okay, so I think that's it.
Good job. All right, so we have a fair amount of time then for discussion now. Peter, would you like me to keep track of people, or do you have more questions?
Sure, go ahead.
Yep. Yeah.
I would like to ask a question which is very explorative. And I would like to think about the whole question when we consider that whether there's a possibility of non-mechanized knowledge or non-mechanized mind. How do we go about establishing it? Okay, what kind of method we will use to establish it? And it seems to me that in a certain way, the way that you went about analyzing whether we can establish something like this or whether we cannot establish something like this is that you mechanize this very question. And you ask, okay, so I can formalize what Penrose said, Penrose's argument, which means I can put it as something that can be done not by an unmechanized mind that can go beyond algorithm, but I can ask it by an algorithm. I can turn the very question into an algorithmic question, and then when I considered it as an algorithmic question, I see that I cannot prove it.
Yeah, but in showing that I did something non-mechanized.
What?
A little creative flash of insight.
No, so what I'm thinking about is this, that suppose Penrose is right, and suppose we have a mind that, suppose human mind go beyond algorithmic thinking. Then to prove that this is the case, to establish that this is the case, if this is correct, then it's open that there are ways of establishing things that essentially go beyond algorithmic thinking, but don't have to be just a flash of, could be something that we really don't know. It's an open question.
Yeah.
And so why can we be sure, how can we prove that this is not the case by sort of limiting ourselves to the very kind of method that this statement says we can go beyond them? Maybe in order to establish this, if you turn it into an algorithmic question, you see that there are problems, but maybe the very way to approach this problem is to go beyond the kind of way that, formalize it and then look at the formalized version, but really try to understand the heart of what it is or how it is that we can go beyond the algorithmic thinking and then try to use this very heart of the thing to, examine whether it can be correct. So that it seems to me that sort of the way you went about it maybe was sort of self-defeating from the point of view of Penrose, because you limited yourself to what Penrose said we don't need to limit ourselves. So I don't know, just wanted to ask what you think about it.
Okay, I have two things to say about that. One is, it looks like from what you said that what I'm doing is I'm taking Penrose's argument, which is sort of free and open-ended, and then pulling it into like the confines of his narrow formal system, and contorting what he's said, modifying his fundamental concepts, changing some of his principles, and improving some limited results. Actually, that's not what I did. What I'm doing is I'm broadening what he's doing. So he's trying to give an argument that the mind can't be mechanized by using the incompleteness theorem.
By what?
By using the incompleteness theorem. And, he has an informal argument, and it's looks intuitively plausible. And the only way I know of assessing an informal argument is by checking whether it can be made precise and whether it's valid. And it's not as though I just made it precise in one way. I actually handed him a system which makes it precise and is provably consistent. And then showed that even with those assumptions, you're not going to be able to do what you're trying to do here. And then the more general thing, that in fact there's no theory of truth which is going to do this. No known theory of truth. Now it could be that Penrose either A, says, okay, I give up. I realize that when you start going to type-free truth predicate, you have indeterminate senses. You have to be careful. The thing you could try to be proving is indeterminate, or you might have an independence result, like you've shown. Then you could take a different tack and try to, show that the mind can't be mechanized by using the old quantum gravity argument. Sort of quantum collapse happens in our mind, and that's the heart of free will. And, there's a lot of different approaches that you can take. So I'm just taking this one approach, helping him out, broadening the terrain, and showing that it's fundamentally limited. So try a different approach. And there's, multiple approaches. Rick was pointing at some in terms of being able to understand abstract objects. There's the quantum collapse approach. But if you were to if you were to push on any of those approaches, then I would try to get a grip on it and see whether it really worked. But if the claim is that don't try to get a grip on it.
No, that's
No, I disagree.
No, that's the only thing.
Since we should move on.
Okay, so we can talk about it later. I just said that the only thing is the question, is there a way to get grip of things which goes beyond the kind of things, the kind of method that you used in order to get grip of that?
Oh, I think there's multiple approaches to it.
No, I mean more in sort of in principle of a different kind, but anyway, I should go on.
All right, Isaac Lee.
Yeah, I just wanted to, for point of clarification, I've been, plenty of people are interested in belief change and belief revision, and they study deductively changes in deductively closed systems. Now, there is some lesson that must be learned from all of this, or there is some issues that must be respected here. But if I understand you correctly, it isn't going to change a hell of a lot, because as long as I keep truth value parts of this, to talk about the rechange in those terms, everything will continue as hopefully as it has been. At least the issues will remain the same. We don't have too much to worry about. As long as we don't worry about tinkering with massive changes in mathematical.
That's
Is that, you understand what my worry is?
Yeah. Yeah.
You repeat the word. The word. There's a lot of discussion of belief change these days, and formally it's usually done in terms of transformations into deductively closed theories. Chiefly because we're not going to be worried about changes in mathematical belief in these theories. That's what you're foreclosing by doing that. What I was wondering, as I was listening to this excellent discussion, I was wondering whether there was any strong or super restriction that people who work in this area would have to respect in order to continue, or whether they are out of business. And that's the question.
So you're saying what would happen if you, instead of...
You're just talking about mathematical theories that might change. But if I add to the mathematical theories, physical theories, biological ones, with whatever mathematical structure they introduce, it's not likely to be not likely to be altered much by what you're saying.
No, I don't think so. That would be taking, so the systems have three parts. They have the system of arithmetic, and then they have knowledge, which responds to that, and truth.
That's right.
And then what you're saying is take the base part, arithmetic, throw in physics, biochemistry,
Yeah.
and so on, and then have these two tiers above.
That's right.
Would the results change? So you are strengthening the theory, and there's a hope that that additional stuff will be to do it. I don't think that's.
I'm hoping that the story gets no worse than what you said.
Yeah, I don't think it'll change if you throw in exact science. But something interesting could happen if you threw in probabilistic information. So Godel actually did think at one point that although you could never prove that the mind wasn't a machine, you might have probabilistic information that it wasn't.
Well, I won't get into that. There's a story about that, but I suspect that's not going to matter. It may matter in the sense that some physical theories are statistical theories, and may want to work in that sense. But usually then probability is treated as truth value, whereas if you're thinking about confirmation, evidential support, and so on, at least the people I like to frequent with don't think of probability judgment as truth value at all. So that automatically raises another set of issues. But not truth value, not because of the sort of paradox that they were. Creating the paradox.
Peter, could you perhaps say something about Gödel's own attempt to argue not for this first disjunct, but rather for refuting the second one?
For refuting the second one?
Yes.
Yeah, so to refute, the second one is that there are absolutely undecidable sentences, and Godel thought that there weren't absolutely undecidable sentences. I'd say a bunch of things about that. The first thing to say is a very general thing. When he characterized this, the philosophical significance of the disjunct, he often said that the first disjunct is associated with the superiority of reason over computation, and that the second disjunct is realism. So he could either show that mind transcended matter or mathematical realism. And the second disjunct, the reason he thought that was associated with realism is because it would show that there are mathematical truths that are beyond the reach of the idealized mind. And so there must be this independent third realm. But now he didn't believe the second disjunct, but he was still a realist. So what's going on there? The reason is that he was a realist, but of a different variety. He was both a realist and a rational optimist. So he had a different argument for realism. So it's a bit misleading. He said, this disjunction shows that either mind outstrips matter or realism holds, and then quietly he says on the side, I don't believe the second disjunct, but he still believes realism, because he had a different argument. What was the argument that he had for the second disjunct? Well, as an article of faith, he was just a rational optimist. That's one. And he also had circumstantial evidence because he happened to be Kurt Gödel, who could solve lots of problems. But what did he have to say about it apart from thinking that it was true? There was something he said. He said he tried to characterize in the Princeton Bicentennial paper two things. He dealt with absolute definability and then absolute provability. And for this, he suggested ordinal definability, which he wanted a notion of definability that you couldn't diagonalize out of. So for every notion of definability you pick, if you're precise about it, then there's going to be a least ordinal which is not definable according to that. But then you're going to be able to define that ordinal by saying it's the least ordinal, which is not definable according to your notion of definability. And that gives you a richer notion of definability. And he wanted one which was robust, that you couldn't diagonalize out of. And so that argument shows that you have to make all the ordinals definable if you're going to have a hope of doing it. And it works because ORD is ORD. And there's no contradiction. So that's a good candidate for ordinal definability. And then for this, he wrote it was ZFC plus true large cardinal axioms. So he noted that what's going on when you climb up the hierarchy of systems is you're able to prove the consistency sentences of the previous system. And a very strong way of climbing up the systems is by climbing up the hierarchy of sets. So PA is down here, and the second order PA is here, and third order PA is here. And then you have ZFC. And then it just keeps going. And then you've got super compact cardinals and things like that. And he wanted to take, let's just throw in all the large cardinals which happen to be true. So throw in the stem. Just like in this case, you were throwing in the ordinals. Now you're throwing in the large cardinals. Grant yourself that. Just say that those are your axioms. And then relative to ZFC, maybe you're going to be able to prove all sentences. So he actually suggested this as a candidate for absolute provability. So he said it could be that there's a completeness theorem that every sentence of set theory in mathematics is provable or refutable on the basis of this base theory. Now that base theory is not recursively enumerable because you're helping yourself to this huge oracle, the stem of all true large cardinal axioms. So that's good. You avoid the incompleteness theorems. There's a hope of doing it. Now, is that a good candidate for absolute provability? And can we say anything precise about it? Well, I have a problem with it as a candidate for absolute provability because of the absolute in absolute provability. The case for the large cardinal axioms as you climb higher and higher gets weaker and weaker. And that's another problem I have with talking about absolute provability or knowability in this unified sense. I mean, justification in mathematics comes in degrees. And as you go up, you're getting weaker and weaker. The case gets harder and harder. So to treat all of that as though it's just some unified thing and say this system is well justified, or this system is evident, or this system is absolutely provable, is a bit of a stretch as far as I'm concerned. Also, what is this system? I mean, I haven't, you can't have an RE characterization of a large cardinal axiom, so you're just kind of gesturing, right? It's a bit of the angelic mind thing. Well, so we can only say something schematic about it. We have a kind of non-RE schematic understanding of what a large cardinal axiom is. Can we say anything about whether he was right, that there would be a conjecture, that his conjecture about this system, which is vaguely characterized, resolving every question? Well, no. There's the Levi-Solovay results, which show that this system, CFC plus large cardinal axioms, does not prove CH. It does not prove not CH. So CH is a funny sentence in that its independence is robust. It remains undecidable even when you add these large kernel axioms. So can I say that his conjecture is false? Well, what I can say is, to the extent that we understand his conjecture, it's false. His conjecture is schematic. We have a schematic result, which scales up with it. Whether it scales up perfectly, you can't say because they're both schematic. So.
Well, can you say a word about how this Levy thing characterizes that LCA in order to show these independence?
Oh, that's why I put scale quotes around here. So what you do is you march up. So they did it for a measurable cardinal and for a theorem. When you do it for wooden cardinals, you prove a theorem. Super compact, prove a theorem. So we keep proving these theorems, but maybe one day we're going to hit a block. I mean, I've been investigating ones which are right up here. Drawings not to scale. Which may get around the Levi-Solovay. So there's that possibility. Yeah.
Just a little side thing on that. So are the proofs we have of the versions of Levi-Solovay analogous, or are they very different as you climb up?
Some of them change, yeah. There's some which are routine, so it'll be a routine proof for a stretch, and then a new idea will be needed.
So new ideas are needed. It should be possible then that once you climb high enough, there will be exception.
That's a good. But people have a feel for it, right? There's a kind of standard way of characterizing large cardinal axioms, and they have a feel for the proofs. And the intuition of most set theorists is that this is going to be persistent. And there's a fundamental problem, and something quite different than large cardinal axioms is going to be needed.
Until some new idea, like Wooden's, comes along and changes the game.
Yeah. I mean, you could fold that into the base theory.
We don't, but we can't know in advance what the new idea. I mean, I was thinking in respect to Rick's question. Let's think of the idealized human community that has an infinite history into the future and continues to do mathematics.
Yeah.
So it is just us, but we put all of us idealized into the future.
Yeah.
And we assume that we'll always be here. And we're going to continue to learn more and do more mathematics and have new ideas and new ways of proving things. And so we can't anticipate that, and we can't anticipate it on the basis of how many particles there are.
Okay, this gets really so let's just do this. So we assume time is infinite, and we find a way of getting away from the sun when it does its thing, and
we just go out somewhere else.
Yeah. So we keep bouncing around, and we keep collecting energy, and we live forever. Okay. Then we start generating theorems. And the question is, are we going to generate theorems that would outstrip a Turing machine? Now, there's a problem because there's going to be a bound on what we can do. So we're never going to be able to generate theorems that are longer than 10 to the 10 to the 10.
But, I mean, here we're already not a Turing machine because we have a non-RE theory, right? Or am I
What do you mean we? You're talking about the large
Well,
cardinal.
suppose we start investigating this kind of system. And now we're investigating something with a strongly non-RE notion. So doesn't that mean we're not in a mechanistic?
No, there's a difference between saying that. I mean, I'm saying consider the true large cardinal axioms, but I haven't told you what a large cardinal axiom is.
Right.
The ones in Ken and Moore's book are RE. I mean, the description, because it's finite. There's only 500 and something pages in it. I'm not sure I understand what you're saying. So
we may come up with new ideas, and we may come up with ideas that aren't large cardinal axioms, but allow us to do more than we could do before. And we can't anticipate now what that might be.
But there's still going to be a bound on the theorems you can write down. So fix your language, the language of set theory. There's going to be a bound on the length of the theorems that we could write down. It's going to be less than 10 to the 10 to the 10. I mean, there's a way of getting around it, which is what I was going to get at. So you want to get around the bound. So you assume that we evolve to the point where we've got greater and greater capacities without limit. Okay? And then the question is, if you look at this collecting people, proving these theorems that are getting longer and longer, whether the path of theorems that they output is non-RE. So at any finite stage, it's going to be RE. The question is whether the path is going to be non-RE. And then the sad fact is we're never going to know.
Right.
Because at any point, we're going to be on the tree.
Right. That's good, isn't it? I mean, we can't know the future with any kind of certainty.
Okay, so I will grant that it is possible that the human race continues forever, gets more idealized without bound. I don't Actually, I don't believe it, because here's this is going to get really fantastic, but a plausible
We
assumption.
get faster and faster computers, we get quantum computer computation to
They have
work.
to get bigger. They can't keep getting smaller because of the Planck constant, so they're going to have to get bigger. But eventually they're going to collapse into their own weight. So there's,
Eventually, we're not in quantum theory anymore, and we're in some other.
anything's possible once we get to this stage.
But I suppose if you want to get a refutation of the second disjunct, then we have to assume that it's false. Because we are already at a stage, or will be at a stage, where we are not bound in this way.
I'm sorry, I didn't.
But I just wanted to say, if this argument and other arguments can be carried through, well, then we would have a refutation. If not, then at the moment at least, we would have to presuppose the thing we want to establish in the first place. Okay, that's it.
I mean, as a working hypothesis, I suppose there are no absolutely undecidable sentences. And I have rational, I'm a rational optimist that any problem that we can articulate, we're going to be able to find a way to resolve it. But I mean, just tell you as an article of belief, I believe that all the sentences are set there are determinate, and I believe that we're not going to encounter one that we're not going to be able to solve. But the point that I'm making is just that they're all very small.
I understand.
Yeah.
Several people on the list are, but Charles, did you want to ask a question?
I think a lot of people have a feeling that we don't quite understand what we're talking about because of the nature of the model that the models that are available. Starting with the idea of the mind as a Turing machine, I'm not sure we quite understand that. A more real, maybe more realistic kind of a physicalist picture of the mind would bring in a lot of physical theory about how the brain works, and knowledge about how the brain works. I don't think we're in a position to prove theorems of mathematical logic about the implications of that, but maybe Peter thinks the implications of that idea because it would, for one thing, it would probably involve a speculation about the implications of a theory that we really don't have and are quite far from having.
Yeah, well, there it falls through my fingers.
Pardon?
There it falls through my fingers because we don't have a good model beyond the Turing machine. So there, I feel like we're talking about the angelic mind, and once we start talking about the angelic mind, pretty much anything goes. But the only one way in which we can make it precise is this very general way, looking at the lines that people like Lucas and Penrose have put, and that fails.
All right, so we still have several people on the list. Did you want to follow up on that, Charles?
No, I think I'll leave it at that.
Okay. Daniel, you
I just
had
want
your hand up for a long
to hear a
time.
bit more about, you said in passing to Isaac that Godel body might have an argument that we're probably not machines.
Yeah. I'm not hearing anything about that.
That's at the end of Mathematics to Philosophy.
Yeah. Where he's talking about. Yeah, he's talking about biology and.
Formation of the mind on a geological timescale.
Yeah, I can't reconstruct some passages for those reasons. He did think that we'd actually be able to prove it, pure and simple. But prior to that, I think he thought we could collect inductive But, I mean, it's very vague. He just mentions neuroscience, biology.
All right, we've been going on for a long time, so let's draw a line here, but take the two last questions on my list. So Mark first.
Yeah, it's a remark really, from a very different point of view, intuitionistically. There is the, of course, they have an argument that there are no absolutely undecidable propositions that exist in two flavors. There's a Brouwerian one and a Martin Luff, but they are of course very similar. But there's also in the theory of the creating subject, Saul Kripke devised an effective but non-recursive function.
Pardon?
Saul Kripke gave against the background of the theory of the creating subject, he gave an example of an effectively computable but non-recursive function.
Can you tell me what it is?
Yeah, I mean, I can write it down, right?
So, against the background of the
The theory of the creating subject.
theory of the creating subject.
That sounds more exotic than it is, but I'll send it.
So, the theory of the creating subject must have non-RE content, no?
That's part of the.
So, you're helping, I mean, if I help myself to 0 prime or, 0 sharp, I can give you a non-recursive thing.
But it depends, of course, on the conception of truth, the concept of truth that you have. And that's certainly a very different one than classical one, or even constructive but not creating subject theories.
Yeah, but what's going on is you're sneaking in an oracle, right?
No.
In the theory of the creating subject, there's some non-RE content that you're accessing.
Well, I'll send you the argument.
I mean, it can't, you just said it can't be RE.
No, but so what you do is, roughly how it works is you take some set of which you know that it's RE but not recursive.
Mm-hmm.
And then you consider proofs that a certain element is not in that set.
Mm-hmm.
And then you have this very characteristic axiom in the theory of the creating subject saying that if the subject if it is true, then the subject will prove it at some point, and if it's not true, then the subject will never prove it, of course. But it's the first direction, which is a special one. That does most of the work. And then you can, on the one hand, you can show that for the creating subject, this function is effectively computable.
Yeah. I mean,
And if you assume that's recursive, then you get a contradiction.
Well, I'm questioning whether that violates the thesis that effective computability coincides with computability, with RE, because it depends on what you put into the creating subject. So, there's lots of non-RE functions that have an oracle, like help yourself to 0 triple prime or help yourself to 0 sharp. And we have a really good grip on that.
I think we should end that bit, and you could continue that later, and do the last question, and please keep it short, since we have been going on for a very long time.
So one of the things it's not like you were just suggesting is that you have this alternative. Either you have a Turing machine model of mind or angelic model. You don't really want to say that, do you? Like, those are the only two alternatives.
No, what I'm saying is that
you've got. I mean, because it looks like
no, that's not what I'm saying. I'm saying that at the present moment, I don't have a model of the mind,
right,
which allows computations like the length of skews number, apart from things like the model involving a Turing machine. But do you have a model of the mind that goes beyond Turing machine, is not an unknown like the angelic mind, and which is not obviously computable by a Turing machine? Because if you do, then...
No, I don't have a theory like that, but I think there are theories that are like that, or theories of progress that are being worked on that are like that.
Like in neuroscience? Or?
No, not in neuroscience, because I'm thinking of the background as being, it's more like Gödel's own argument, which I think is different from the Penrose-Lucas arguments about minds not being machines. I think the Penrose-Lucas arguments don't capture what's going on with Gödel's own arguments about minds not being.
Well, it captures his arguments in connection with the disjunction in the argument for the first disjunction.
Sorry?
It captures all the things that I quoted. I mean, there's many things in Godel, right? There's the variety of argument surrounding the disjunction, and all of those quotes were from Godel, and they pertain to this, and they were on topic. But then there's other arguments, and so I guess you're saying that you're more convinced of the other arguments.
Yeah, I think they get more traction than the Lucas-Penrose argument. I mean, Lucas-Penrose argument is one way of reading the disjunction, but it seems to me that maybe that's not Gödel's way of reading the first disjunct in the disjunction.
Oh.
That is, he's going to have another way of arguing that minds are not machines.
No, it is. I mean,
Well, it's the thing that I mentioned.
just look at the proof of the disjunction that he gives. It's the proof that I gave.
Yeah, so what I'm thinking is, well, he says in certain places that, what I'm thinking of is a comment I made before, namely that if you have access to abstract objects, and that's really a key part of the argument. I don't see that playing over the same kind
It's
of
not a
role.
key part of the argument for the disjunction.
Well, I don't see it playing any role at all in Lucas-Penrose.
I think we should continue that bit informally afterwards, and thank Peter again at this point.